So a couple of things that you guys will need to understand in order to, if you go back to general chemistry, you need to know what um, reduction is, and you need to know what an oxidation happens to be. And I'm just going to mention it here because it's critical for you to comprehend the vocabulary that we're going to be using in this particular chapter. Reduction is when the electrons are added to a metal or a polyatomic ion. And the reason why it's called a reduction is because the negative charges build up, okay? An oxidation is when the electrons leave an element or polyatomic ions, so that now it's positive. So oxidation means that the charge goes up, reduction means the charge goes down. Now, remember that the only way we can change the charge of a chemical is by changing the number of electrons. If you change the number of protons, you don't have that, you don't retain the identity of the chemical. So in electrochemistry, all we're simply doing is changing the number of electrons. So that's critical. If just make sure I have this correct. Okay, that's critical if you guys want to do electrochemistry, is that you can only change the number of electrons and you don't ever change the number of protons, because once you do that, then you change the identity. So you make the charge bigger by removing that electron. And so the charge goes from like 0 to +1 or +2, depending on how many electrons you remove. And so that's the oxidation. So when a chemical loses electrons, we have an oxidation, okay? Think of it as lose electrons, oxidation. The acronym for that would be LEO. LE, lose electrons, oxidation. Now, when you gain electrons, your charge builds up. It becomes more negative. So that's a reduction. So when you gain electrons, it's reduction. So the acronym for that would be GER. So I have, in one of my slides, I have Leo the lion saying GER. And so you can't forget which is which, okay? The other thing you should know is the oxidizing agent and the reducing agent, okay? That's also discussed in my previous slide. Oxidizing agent is responsible for the other partner. Oxidizing agent is responsible for oxidizing its partner. So an oxidizing agent has to remove that electron from its partner, okay? In order for its partner to oxidize, it's got to pull that electron in. So an oxidation agent is a chemical that gets reduced because it's responsible for pulling that electron and oxidizing its partner. Now, a reducing agent is responsible for reducing its partner. In order to do that, it has to supply it with electrons. So reducing agent is a chemical that undergoes oxidation because by giving up its electrons, it's oxidizing its partner. Yes, very confusing. Electrochemistry is confusing because the electron charge is negative, okay? An oxidizing agent is a chemical that is reduced. A reducing agent is a chemical that gets oxidized. You just have to remember that, okay? So let's go ahead and look at this. So we're looking at, this is a classic example. And for those of you who watch like the few episodes of Breaking Bad, you saw an episode where the guy built a battery using pennies and zinc. Well, you can actually build a battery if you have these raw material. In fact, you can build your own battery using a lemon and a penny and an iron nail, okay? And basically the idea is because electrons want to flow from one species to the other. And whenever you can have electron flow through an external circuit, guess what? You have electricity. And if you have electricity, you can do work, which is basically a battery. So In this particular case, what you have here is an example in which you take a zinc strip and you put it in a copper solution. Copper ions are always blue. Copper +2 ions are always blue. So what you see here is copper ions in solution. And what happens is that there's going to be a chemical reaction that takes place in which the copper +2 goes to copper 0. So the copper +2 is being reduced because its charge is being lowered. The zinc, however, is getting oxidized because now the zinc is going from 0 to +2. So here you know which is the oxidizing agent and which is the reducing agent. And this will happen because there is a driving force for electron to transfer. Okay, there is a driving force for electron to transfer. Now, if we can take the electron transfer process, remember that the electrons are being removed from zinc because it's getting oxidized. So it's losing electrons and being transferred to copper because it's getting, in copper case, it's being reduced. It's going from +2 to 0. Well, if we can take that electron and run it through an external circuit, then we can take advantage of the electrons moving through an external circuit, and then we have a battery. So this is a movie that kind of shows that. I don't really have time to show that movie, but you guys can see it. It basically just shows you the electrochemistry reaction that takes place. Okay, here's the cell again. And now we separate the two reactions, and we call these cells. We call these cells because they have their own isolated chamber and they're doing their own chemistry in isolation, but being connected through an external wire so that electrons can be shuttled. So here, the zinc is going to get oxidized. And you know how many electrons are going to be produced per mole of zinc. Okay, there's going to be 2 electron transfer, and that's going to go to the copper. And if you just have this particular setup, what will happen is that initially the copper will get oxidized and then it'll stop. And the reason why it stops is because you're going to get charge buildup in this particular cell. The cell is going to have a charge buildup as well. And whenever you have a charge buildup, if there's no way for you to kind of neutralize that, then there's a barrier there that the electrons can't overcome. So this will work, but it certainly will stop because of the fact that you have charge buildup. So how do we cause this apparatus to have no charge buildup? Well, what we can do is we can put in a salt bridge. Okay, so this thing again, just show you that there's going to be a charge buildup here. Here we add a salt bridge, and a salt bridge is just a way of connecting not the electrons, but the ions. What happens here is that the zinc is going to produce electrons. The electrons are going to go to the copper, but now because of the excess negative charge that's built up here, we need a way to neutralize that. So if you have a salt bridge, and a salt bridge really is nothing more than a link, a bridge that connects the two cells, but with ions. Because this is negative, what will happen is that the positive cation is going to go towards that cell and neutralize any negative buildup. On the other hand, because you're removing electrons from this cell, this will have a charge buildup of positive. So the negative ions are going to go towards that particular cell. So this way, what will happen is that we have a closed circuit. It's the same idea that happens when you have, when you turn off your switch in your room, okay? When you turn on the switch, you close the circuit so that electrons can flow from basically the electrical port to ground. But when you turn it off, it opens up the circuit. So now the electrons are not going to have anywhere to go. So by removing that salt bridge, you don't have any electron transfer. But by adding that salt bridge, you do have electron to transfer. So this right here is really the what we call a voltaic cell. A voltaic cell produces electricity. And therefore E0 is positive and delta G is negative. It's a spontaneous process. If we were to reverse this reaction, it would not be a spontaneous process. In fact, if we were to try and force this reaction to go in the reverse, we would need to pump in, we would need to pump in 110 volts to drive that reaction in the opposite direction, okay? But in this particular case, we call this a voltaic cell, also known as a galvanic cell. Okay, galvanic cell, voltaic cell, batteries. That's what they are. They just have historical names. The galvanic is named after someone who worked with a lot in terms of electricity a lot back in the 1700s. Okay, now I want to discuss the features of a voltaic cell. The features is that basically you have two conductors. You have two sources. You got one that is going to produce the electrons and one that is going to be accepting electrons. By the way, you cannot have a redox reaction. That is a reaction in which one chemical gets oxidized, another chemical gets reduced. You cannot have a redox reaction if you don't have a partner that will accept the electrons. If you got a chemical that is undergoing reduction, okay, remember reduction is you gain electrons, then it needs an electron source. Theoretically, you can still think about a reduction by pulling electrons from the air and do that calculation, but in reality, you need an electron source, and so they always have to be paired. Okay, whenever you have a redox reaction, there's got to be a species in there that is going to lose electrons, oxidize. There's got to be a species in there that will gain that electrons. If you have no species in there that will gain that electrons, the reaction's not going to go. Okay, so we like to say that they are coupled because they have to exist in a pair. So we have two conductors. Right here, we have an electrolyte solution. That's generally the solutions in these cells. And that's because what happens is that when like metals, and you don't really need metals, you can have two species that are in aqueous solution, but you undergo oxidation between one species and the other. But in this example, the zinc is going to get oxidized. And if it's going to get oxidized, you don't have anything such as a zinc plus 2 solid, okay? There's no such thing as a zinc plus 2 solid. Zinc plus 2 can go into a medium, an aqueous medium, and you need a counter ion to that. So zinc plus 2 and sulfate are the species there. That would be your electrolyte. In this particular case over here, you've got copper plus 2 and sulfate as well. So you have to have an electrolyte solution. You need a salt bridge, and the salt bridge has to be porous so that the ions can migrate through. Okay, so for a voltaic cell to happen, you have to have this component. This is just a voltmeter, by the way, and it measures the potential for that electron to be transferred. Okay, it basically measures the potential for that electron, basically measures E0. And under standard state conditions, that's why I have that super zero right there, the electron transfer between zinc and copper and the electrolyte's 1 molar solution is going to be 1.10 volts. Okay, the electrons need to be transferred via an external circuit, and salt bridge has got to allow the ions to migrate. Okay, the place where, remember, this is where zinc goes to zinc plus 2. This is your oxidation, because the zinc species, which is your reactant, is losing its electron and becoming the product of zinc plus 2, well, that's your electron source. That's your electron source. Okay, that's your electron source. And all oxidation process are called anode. And you can remember that because anode and anions are very similar, and that's where the electrons originate. On the other hand, on the other side, this is where the copper plus 2, that's the copper in solution, is going to convert over to copper 0 and start plating out on that electrode. Okay, this is 0. Well, that is where the electrons are going to be accepted, 2 electrons for every 1 copper plus 2. So the electrons are going to be attracted to the positive because opposites attract. Okay, that's why it's called the cathode, positive. Okay, positive. So where the reduction occurs, this is the reduction right here. Okay, this is the reduction right here. Where the reduction occurs, you have the cathode. Where the oxidation occurs, you have the anode. The anode's negative, the cathode is positive. And then the other thing you need to remember is that the anode is black and the anode is red. And that's generally what you see in a battery. If you ever look at a battery, like a car battery, red on positive, black on negative, okay? So that's basically it. If you look at your AAA batteries or D batteries, the positive is called the cathode, the negative is called the anode. And that's because these things are batteries. So to move out of that, to make sure that you understand the nomenclature of a voltaic cell, okay? Again, these are the special features that I just mentioned. For the anode, these are the special features for the cathode. So it's basically a summary of what I just talked about, okay? Here it is again, zinc, oxidation, reduction. Here is the negative terminal, anode, the positive terminal, cathode, and the question is, how did we get 110 volts, okay? The way you determine the voltage of an electrochemical cell is you need to understand what reaction is occurring at the anode and what reaction is occurring at the cathode. And in this particular example, you can see that the reaction here at the anode is your zinc going to zinc plus 2. And under standard state conditions, in other words, if you have an electrolyte that's 1 molar and your zinc is pure at 298 degrees Celsius, 1 atmosphere, then you can find an electrochemical potential. And this is found in the back of your book because it's generated for you. Your experiment 8, you guys are actually going to generate an electrochemical potential table as part of your experiment, okay? But these are set, and under standard state conditions, they're going to have a specific value, okay? And then the cathode here is a reduction, and that's copper plus 2 going to copper 0, okay? Here, of course, we need to balance this, we need 2 electrons here, we need 2 electrons here. A lot of times, we do a shortcut. We basically just do this. That's the oxidation. This is a copper reduction. Okay. Sometimes we just do that in terms of a shortcut because we know that that's the species that's undergoing oxidation. So it's going to be the, in this particular case, the anode. But this also has a potential. And if you look it up in the back of your book, what will happen is that you'll find the reduction potential of copper. And the reduction potential of copper is about 0.34 volts. However, you will not find the oxidation potential of zinc. You will not find the oxidation potential of zinc. You will not find that. What you will find is the reduction potential of zinc. okay? You'll find that. And when you look up that value, it's going to be given to you as negative 0.76 volts. It's actually a negative. So the zinc undergoing reduction is actually not a spontaneous process. The copper undergoing reduction is a spontaneous process because of its positive. But this right here is not that. It's the reverse of that. It just so happens that in electrochemistry, if you reverse a reaction, then you change the sign. Okay? Remember, in electrochemistry, if you reverse the reaction, you change the sign. All the electrochemical potential found in the appendix or in the back of my lab manual or in that equation page are based on standard reduction potential. Standard simply means that it's under standard state. So it's going to be a super zero right here. Reduction tells you that they're always written in terms of their reduction reaction. That is, they will start gaining electrons. That's the reduction. Potential just means that there's a certain voltage that is going to be that's going to be documented for that particular reaction. So the fact that we don't have the oxidation reaction, but we have the reduction reaction means that this now has to change signs to positive 0.76 volts. And when you do that, okay, when you do that, then the total potential would be, because the reaction is zinc undergoing oxidation and copper undergoing reduction. So all we've got to do is add these right here, and that comes up to 1.10 volts. Okay, so you can see it's pretty straightforward if you know how to read tables. Okay, now this is for standard state conditions. 1 molar solutions, 298, 1 atmosphere. If it's not standard state conditions, then we need to apply corrections, and we'll talk about that next time. But this is the potential for that reaction, and that's why you read 110. It's got to be standard state, however. Now, this is the method I prefer when I want to calculate the potential for a reaction. I just make note of what reaction I have. I separate the oxidation from the reduction. I look up the E0 value for each. For the oxidation process, because in the appendix, it's written as reduction, I change the sign, like right here. I change the sign, and then I add the 2. And when I add the 2, the net reaction here is zinc 0 plus copper plus 2 goes to zinc plus 2 plus copper plus 0. So that's the net reaction that occurs, and this is the voltage that is read. Now, I want to make sure that you don't get confused, because when you read your book, what will happen is that it'll give you an equation. And that equation is basically this idea right here, that you're taking the potential based on the chemistry that occurs, and then you're adding it up, okay? So this is my method. This is like method 1. This is my method, and it's easy to remember because you go back to the chemistry and you look up the potential in the back of the book, and for any oxidation reaction, you just reverse the sign, okay? Now, the back of the book will have this equation. Okay, this is what I just did. This is the equation that the textbook and most textbook have. Okay, it's basically the same thing that I just gave you. The E0 of the cell, which is 110, is equal to the reduction potential at the cathode. That's going to be this right here, 0.34. Minus, the minus here, okay, will change the sign of the reduction potential at the anode. So if you look up the reduction potential of the zinc, it's going to be negative 0.76. But the negative in front of that, let me just show you that real quick, that negative right there changes that sign. So a negative and a negative makes this whole thing positive, makes this whole thing positive. And then all you got to do is add up those equations. So 0.34 minus a negative 0.76 is actually 1.10. It's the same idea, but if you just use this equation blindly without understanding the process by which these two techniques are related, you're always going to be off in your calculation. You either use one technique or the other technique, okay? You either use one technique or the other technique. I've seen too many times where you mix your technique. A lot of you will say, oh, this is an oxidation, so I'm going to change that sign anyway to positive 0.6, and then you subtract the positive 0.6. It messes up everything, okay? These values right here are based on what's found in the appendix. The appendix will give you negative 0.76, so just write it as is, and the negative there will change that to the positive because now it's an oxidation. So that's why it's the oxidation, the reduction, that's your final state of where the electron goes, minus the oxidation, that's where your electrons originate. It's always final minus the initial. Final minus the initial. Cathode minus anode, okay? But if you do it via my method, where you break up the two half reactions, figure out which is the anode, and then change that sign because you know it's an oxidation, then all you've got to do is add it together. Please don't confuse the two ways of doing the calculations. They're both correct, but a lot of you will end up mixing the different methods. Don't do that, okay? That's a common mistake that you're going to kick yourself in the behind in this next quiz because you're overthinking it. That's what you're doing, you're overthinking it. Stick to one method, okay? So what's going on here is that you basically have why do the electrons flow? The electrons flow because there's a driving force for one species to get reduced, and there's a driving force for another species to get oxidized. There's a driving force for the electron transfer to occur, okay? And remember that the anode, anions, is the negative. It's going to be your most negative reduction reaction, and your cathode is the positive. And it's always cathode minus anode in this particular case. The minus changes that sign at the anode because that's where oxidation is occurring. Yes, it's very confusing. You got to hear it again and again and again because the reason why it's confusing is because we have the electrons that is the main actor, the main player in these process, and the electrons are negatively charged, okay? That's why it always seems like it's opposite. And when you get into the problems, you're going to find out that you're mixing your signs or something. Just remember that electrons are negative. That's why it seems like it's opposite. So let's take a look at a different reaction, okay? Let's take a look at the zinc undergoing oxidation. So zinc undergoing oxidation, that potential under standard state hasn't changed. It's 0.76 volts, okay? The reduction is minus 0.76, but the oxidation is positive 0.76. And let's say we couple that. Remember the word couple, meaning that we pair it with a chemical that will accept the electrons, okay? And in this particular case, we're gonna couple it with the hydrogen reaction. H plus going to H2, okay? Don't write this. Hydrogen never exists as an individual element. The way we find hydrogen in nature is H2. Remember your diatomic chemicals. That's why we have two H plus here, okay? It just so happens that if you wire this voltaic cell up, okay, if you wire it up, and have your cells in here, like what you have right here, where the electrolytes are 1 molar, and you put a voltmeter there, okay, you're going to read 0.76. Now the question is, well, isn't that the potential for zinc anyway? Yes, it is. And the reason why it's 0.76 is because, remember, only entropy has an absolute scale. Well, temperature has an absolute scale as well, but entropy has an absolute scale. Electrochemical force, that's the E0, is also a state function, but that doesn't have an absolute scale. We have a reference point, and our reference point in electrochemistry is this reaction right here. It's this reaction right here. We assign that as 0.0 volts, and if we couple any reaction with the hydrogen reduction, H plus going to H2, then whatever volt we read is based solely on that other chemical, because we assume that the hydrogen is 0 volts, okay? We have a reference point. We have a reference point. So that's why you see 0.76 volts in this particular case. The reaction in which hydrogen ions goes to that, or this goes to hydrogen ion, that is both 0 volts, okay? Because if you take 0 and reverse it, it's still 0. So that's going to be our reference. That's going to be our 0 value. And now we can create tables, because if we start coupling two electrodes, two cells, one's undergoing oxidation and reduction, and we only know one of them, and we can measure the net result, then we can calculate the second one, okay? And that's basically experiment number 8. You guys will be given a reduction potential for zinc, and then you're going to measure the voltage when you couple it with other metals, and then you're going to create a standard reduction potential in experiment number 8. And in real life, that's what we do. That's how we generate the standard reduction potential. In the back of your book is we basically have a starting point. That's the hydrogen oxidation reduction process. We make that 0. And then when we start coupling the hydrogen with all the other reactions, then we can measure its voltage, its ability to transfer or accept an electrons. And hydrogen will either deliver in electrons or accept electrons depending on what it's coupled to, okay? So this is how we sort of build that. And this is what it looks like. This particular case, you notice that hydrogen is not a metal. Hydrogen is not a metal. So how do we facilitate electron transfer for chemical that's not a metal, like hydrogen and hydrogen 2? Well, we don't have hydrogen 2 as a metal, but we can bubble hydrogen 2 into the solution so that now H plus and H2 are in contact with each other. All we really need for this reaction to take place is some sort of electrode that is inert. We need an inert electrode. And what that simply means is that you need some sort of material that will simply facilitate the electrons so that the reaction can occur. And what are good inert electrode? Platinum, okay, palladium, copper, graphite are good electrodes. And why are these good electrodes? Because it takes very, very high voltage for these things to get oxidized or reduced, okay? And so they're not going to want to give up electrons or anything. They're just going to shuttle that electron to its destination. And so this particular metal right there happens to be like a platinum surface, or you can have a platinum wire. But basically, you do need to bubble in hydrogen, because remember, your reaction's H plus and H2. Okay, so you got to bubble in hydrogen in there at 1 atmosphere. So that's what's going on here. This is your anode. Zinc is still undergoing oxidation. Hydrogen is what's accepting the electrons and going to H2. It's undergoing reduction. Your net reaction is this right here. And your E0 under standard state is 0.76 volts. And if you do the cathode minus anode, let me just show you that. If you do the equation as done by the textbook, E0 cell, because this is our cell right here, is equal to the E0 at the cathode minus E0 at the anode. And these are your reduction potential, So the reduction potential for hydrogen is 0. Your reduction potential for zinc is minus 0.76. So look what happens. 0 minus a minus 0.76, that's positive 0.76. That's exactly what we have right there. Okay, so you can use that equation. But basically, it's because zinc is still undergoing oxidation. That's a positive 0.76, and the hydrogen is 0. Okay, so I need to introduce you to a line notation. And the reason why we need to know about line notation is because it's very tedious to always draw these cells when we're referring to electrochemical reaction. And if you look at your electrochemical activity in lab, it's going to ask you to do line notation. In fact, you guys should take a look at that after this discussion, because you could probably answer some of those questions. So in terms of the line notation, what we have in the line notation is we denote which species is the anode, which species is the cathode, and the chemistry that occurs. So in a line notation, you always write the anode first, followed by the cathode. So whatever occurs at the anode, you write that, followed by the cathode. You don't need an arrow because I'll show you how the two are separated. Remember, the anode is the oxidation. Cathode is the reduction. Okay, reduction is where the electrons end up, but that's the positive terminal because the electrons are attracted to a positive terminal. The anode is where the electrons are originating. That's your negative terminal. I know, still confusing, but if you keep seeing it, hopefully that concept will be more clear in your mind. So you put a straight line, a horizontal line for phase boundary. What is a phase boundary? When you have a solid and aqueous, when you have a solid and a liquid, when you have a solid and a gas, whenever the phase changes, you put a phase boundary, you put a line there. You put a double line when you have a liquid junction. For example, if you have a salt bridge, this actually might be salt bridge. Okay. Liquid junctions basically where there's the two cells are separated, but needs to be connected by a salt bridge so that you don't have any charge buildup. Concentration of the component, that's generally important. That way you have information of what's going on. And if the concentrations are not supplied, then you can assume, especially if you see this super zero, that it's 1 molar. Okay, because standard state requires that it be 1 molar. So here's our cell again. Here's our cell again, the cell that I showed you, the zinc undergoing oxidation, the hydrogen, actually the copper undergoing, the zinc undergoing oxidation, the copper undergoing reduction. Okay, so how would I write a line notation? Well, the anode is first. The anode is first, and we're going to write the reaction: zinc, solid, phase change, zinc, +2, aqueous. And then we can put in here that it's zinc sulfate, 1 molar. We can say that that particular electrolyte is coming from zinc sulfate. Zinc is +2, sulfate is -2. It's 1 molar. And then we have our salt bridge. That's this part right here. And then we look at our copper undergoing, remember copper is going from +2 to 0. So we're going to see copper undergoing oxidation, reduction. It's aqueous. We can say it's copper sulfate, 1 molar. Phase change, copper solid. That would be our line notation for this cell. See how much easier it is to draw the line notation rather than diagram that cell? Okay. Here, I know exactly what my reaction is. My zinc is undergoing oxidation, +2 electrons. My copper is undergoing reduction. And then I can just write the net reaction. So the line notation allows you to do that. The line notation allows you to do that. Whenever you have a phase change, notice this is aqueous and this is a solid. That's a solid. Then you need that line. Wherever there's a phase boundary, that is, it's connected by a salt bridge, you need that double line. So that's what we have right here, okay? One is the anode, okay, followed by the cathode. Anode first, cathode second. 2 is the phase boundaries. 3 is the liquid junction. You need to do that. Now right here, I put the zinc sulfate here because that tells me it's a zinc +2. I've seen it written both ways, where I write zinc ion and then parentheses aqueous sulfate 1 molar. You need to put that concentration in there to indicate that it's at standard state conditions, because right now I don't know whether that's E, 0, or E. I don't know the conditions, but if I put 1 molar, then I know that it's probably standard state conditions. The salt bridge can be made out of sulfate, sodium sulfate, for example. The salt bridge right here, you could have the salt bridge that I showed you. When you have these things right here, okay, the salt bridge right here, you can make that from sodium sulfate. But the identity of the salt bridge is not really that critical. You just need an inert ion that won't react with these chemicals. Sodium chloride could also be possible. So instead of zinc sulfate here, I'd have zinc chloride, and here I would have copper chloride. So the salt bridge is simply an ionic species that will break up into ions in aqueous medium, okay? It's basically a species that will break up into their ions so that they can flow. Now here, if I blow this up right here, let me show you this, I'll clear this. This salt bridge is not really a tube that connects the two. It's basically a porous membrane right here. And what we have here is zinc sulfate and copper sulfate. And then the sulfates are just allowed to migrate from here to here. And so by the sulfate leaving this area, there's a negative that's going to be being extracted from the anode. You can have a negative buildup from the zinc. Okay, because the zinc will be +2, and what happens is that you have electrical neutrality again. Okay, so there's a migration. In other words, actually the sulfate will migrate this direction. The sulfate will migrate in this direction. So that the -2 will neutralize the zinc +2, and then by the negative leaving this chamber, the net negative can start to accumulate, because when you have the absence of negative, then the positive is going to be your net result. Okay, so that's basically what's going on here. Salt bridge doesn't have to be a tube that is connecting both. It could simply be a porous membrane in which the ions can migrate from one area to the other. And that's what you see right here. Okay, that's what you see right there. So let's kind of take a look at the line notation for some of these. These are what we just talked about. The line notation for this, that was our second example, would look like this. Again, oxidation, reduction. We have 1 molar solution. I didn't even identify the ions. It's not critical. The critical point here is that you understand what is your anode, what is your cathode, and what their concentrations are. So here we have zinc going to zinc plus 2. Here we have H plus going to H2. We have a inert electrode. That could be platinum or it could be copper graphite. Notice that I have a line here, meaning that there's a phase boundary between this aqueous and this gas. And then I have a line here because I have a gas and a solid. So there is 3 vertical lines, and then of course the salt bridge. So that would be the line notation for that cell. Here are other examples. Here we have zinc, and I think the other chemical here is, no, this is what we already covered. Okay, this is what we already covered. This right here is the I minus going to I2. Notice that's the oxidation because it's going from negative to 0. And then the second reaction is MnO4 going to Mn plus 2. Now, how do I know that that's a reduction? Well, you have to know, okay, that the manganese here is going to be, this is MnO4 negative. The manganese there is a plus 7, okay? You have to know how to determine the oxidation state. So review the first lecture for this chapter because it reminds you how to determine oxidation state. Oxygen will always be -2 because it's the second most electronegative element. So if oxygen's -2 and you've got 4, that makes this whole species -8 in terms of oxygen. -8, sorry. Okay, remember this is 1 negative. So this right here tells you it's -8. What plus -8 equals -1? It's got to be +7. That's how you determine the oxidation state of manganese. So please review that. So this right here is the reaction. This is the net reaction. You should be able to write a line notation for that. Here's another one. This one is chromium undergoing oxidation to chromium plus 3. Notice I always write my oxidation on the left. I always write my reduction on the right. This right here is my net reaction. So what are the line notations for these? It's this right here. We already did that. It's that right there. There should be a line right there. I forgot that. And there should be another line right there because that's a phase change. Okay. And notice I'm using carbon graphite as my inert electrode. And then finally we have that. So if I give you this line notation, you should be able to diagram that cell. Or if I give you a cell, you should be able to give me that line notation. Okay. And whether you have a salt bridge or maybe a tube that connects both and have a porous membrane that connects both cell, that would be acceptable. But you gotta have a place where the ions can shuttle between the two cells so there is no net charge buildup. There is no net charge buildup. Okay, so look at these because this is important. Okay, I want to go through this next part in terms of the electromotive force. Probably take about 10-15 minutes and then we'll be done with this section. And then the next thing we're going to do is we're going to skip electrolysis. I'm going to go to the Nernst equation, which really is the heart of this particular section, 19.04 next week. But let me go ahead and finish this part for this particular section. So you might be asking yourself, why do electrons spontaneously travel down the wire? How does a battery work? Why does that electron, how do we get that electrode, how do we get the potential from those chemicals? There is a driving force there, and that driving force is because one chemical wants to lose electrons, another chemical wants to gain electrons. Okay, think of it in terms, if you've ever taken like electricity, maybe you've taken physics, second semester physics, you did a lot of electricity, okay? And whenever you're thinking about electron flow in a wire, they give you the example of water flowing in a pipe. So I'm going to use that here as well. Whenever water flows down the pipe, it's because of a pressure gradient. There's higher pressure on one side and lower pressure on the outside, and that pressure gradient drives that water to flow down that pipe, okay? Same thing in terms of a potential energy. If you have a piece of object at a certain height and it drops, then that potential energy gets converted to kinetic energy. It's what we're doing in terms of these reactions. We're taking chemical energy, which is stored in the bonds and the electrons, and we're converting it to electricity, okay, when the electron starts to flow. So that's the same idea. And again, it's going to be a state function because it doesn't matter how it gets there, only that it gets there. And so it has a certain potential that can occur, and you need to couple these things. You got to have an anode, you got to have a cathode. A species will not just give up its electron if there's nothing there to take it, okay? It's got to be coupled. So this is what we mean by the electrons being flowing, and we call this electron transfer process electromotive force. Its unit is volts, and volts is nothing more than a joule per coulomb. Remember coulomb? It's the unit for charge. It's a unit for charge. So a joule per coulomb is a volt. A joule per coulomb is a volt, and that's what we measure in terms of the electromotive force, the E0, okay? The anode's going to be the chemical that is higher in energy, the cathode's lower in energy, and the electrons goes from the anode to the cathode in terms of the electron transfer. When that occurs, then that energy is released. If you want to drive the opposite direction, then you need to pump in that amount of energy. But depending on the species that you have, that potential is either going to be very small or very large. It depends on the chemical species that are playing this game. And how do you know the magnitude? Well, you look up the chemical formula of the species that are in play, and you look up their E0 value, okay? So here's the scale. And notice I put the most positive potential on top and the most negative potential on the bottom. The most negative potential, these are all reduction reaction. And that's just by the fact that that's the nomenclature we use. In electrochemistry, we always refer to the reduction. So in a reduction, remember, you are gaining electrons. Electrons are in the reactant side. And the species goes from a lower oxidation state to a more negative. Sorry, goes from an oxidation state of whatever it starts with to a more negative. So 0 goes to -1, +2 goes to 0. That's decreasing its charge. The species that will undergo reduction the most favorably is at the top. The species that will undergo reduction least favorably is at the bottom. Notice the negative. That means the least favorable reduction is also your most favorable oxidation. Let me repeat that. Your least favorable reduction is your most favorable oxidation. Why? Because if I take this reaction right here and I reverse that to lithium going to lithium plus, now that potential is not -3.04, but +3.04. Why do you think we have a lot of lithium batteries? Because lithium is one species that is lightweight and gives us the most bang for our buck. Okay, gives us the most potential for the number of moles that we have. Okay, so when you're doing this chart, and this is basically a chart of your standard reduction potential, when you're doing this chart and you want to know which is going to be the most favorable battery, you want to find your most negative, you want to find your most positive, and then couple them. Because your most negative is going to be reverse. It's going to be the oxidation. And now it becomes positive 3.04. And then you keep your most positive as is. That's going to be your oxidation reduction. I mean, your reduction reaction, 2.87. So when we couple these two reactions, guess what? We can make a battery that is 5.891 volts, almost 6 volts. The problem with this battery and why we can't just go in the lab and create it is that we can't contain fluorine gas. Very difficult. So what do? We find other material that will give us more stable species in the reaction. And that's where the polymers come in. If you want a good career for your future, go into electrochemistry, because we're always trying to find better batteries for our electrical vehicle. So that's a really good field to get into in terms of understanding the chemistry of electron transfer, building lighter, safer, higher potential batteries. Okay. So remember, electromotive force is a state function, and it's also an intensive property. What do I mean by intensive? IN means independent. IN, independent of size. It doesn't matter whether you have zinc and you have like 10 grams or 0.5 grams. The potential is still going to be 0.76 if you're going to oxidize zinc. The bigger battery just means that you can sustain that reaction for a longer time, but the potentials are still the same. That's why it's an intensive battery, okay? If you want to change the amount of potential that you get, then you take your batteries and you put it in series. Remember that from physics? If you put batteries in series, if you got a 1.5 volts and you add another 1.5 volts to that, then what happens is that your net electrode is going to be, this is in series, 1.5 plus 1.5, you're going to get a net of 3.0 volts. On the other hand, if you're not so concerned about the size of the voltage, but you want to maintain a longer lasting charge, then you put your batteries in parallel, okay? Hopefully you guys will remember the, you put your batteries in parallel, and when you do that, what happens, of course, is that the voltage doesn't change. It's still 1.5, but then it's going to last twice as long. It's going to last twice as long. So parallel basically doesn't change the voltage. It's still 1.5, but it gives you twice the material, okay? E0 is an intensive property. The voltage doesn't change just because you change the size of the battery. Okay, so let's take a look at this again. So electrochemistry really is a topic that is of vast interest in today's society because we're building better batteries. Okay, again, this is what I just told you. This is what I just said. So when you have a reaction, let's say you have a reaction and you have this, and you look up the potential and you have negative 3.045 for lithium. Remember, the reduction potential is the most negative that we have in our chart. But suppose that in the stoichiometry now, in order for us to balance the equation, okay, we need 2 lithiums in there, 2. Well, does that mean that the voltage goes up twice? I just told you no. because it's independent of size. What really happens is that you multiply the voltage by 2, but then you divide by the number of electrons that are involved, and so you still get the same number as if you had the first reaction. So when you multiply a redox reaction, you don't change the potential. If you multiply it by 3, you multiply it by 8, you multiply it by 0.5, you don't change that potential, because that potential is intensive property. It stays the same. On the other hand, if you reverse it, you do reverse the sign. You do reverse the sign, okay? Stoichiometry does not change the E0 value, but reversing the reaction does change the sign of the E0, the electromotive force, okay? Here's a snapshot of some of our reduction. Again, notice that all of these are reduction reaction. And you know it's a reduction reaction because all the electrons are in the reactant side. In other words, you're gaining electrons, so your charge goes to a more negative value, okay? Reduction. Keep beating that in because it's difficult to grasp when you first hear it for the first time. Here's our 0 point, and everything is relative to that. And here's our more negative. In other words, these guys right here are going to have a more difficult time to undergo reduction. But if you take this species right here, say we take iron plus 2, and we make it iron 0, and we know that potential is minus 0.44. And we couple it with this species right here. Let's say we have sodium plus 2, and going to sodium 0, and that potential right there is minus 0.271. Okay, how can we make a battery from this? Well, we take our most negative and switch it. That sodium is not positive 2, it's only positive 1. And if we switch it, now that becomes positive 0.271. We can still couple it with this reaction right there at minus 0.44. Even though it's negative, we can still drive it by a reaction at the bottom as long as it's going in the opposite direction. The key here is that when you add the two, one of course is the oxidation, the other one's the reduction, that when you add the two, the net potential is positive. Your most positive potential is going to be your most favorable reaction. Okay, your most positive potential is your most favorable reaction. So keep that in mind. So that's how you use this particular table. Okay, that's how you use this particular table. I'm gonna clear this. I think we're wrapping it up here. Okay, this next set just tells you, again, it's to revisit the fact that electrochemical potential is relative. Now, if you guys have either a child or a sibling that was newly born, how do you weigh a child that can't keep still? Well, what you do, and I remember this when my daughter was born, if I want to weigh her, then I can't just put her in a scale, and I don't have one of those doctor scales that I can just lay her on. What I would do is I would step on the scale, weigh myself, and then I would grab her, weigh the total, and then if I just subtract my weight from what's shown in the scale, then I would have her weight. That's the whole idea of this relative scale. Okay, you know what one is, you know what the net result is, and if you just take that difference, you know the answer to the one that you're looking for. Okay, that's what we have right here. So these right here just kind of shows you how the standard reduction potential table is generated, and that's basically just some examples. Okay, so we're pretty much done with this part. Again, you got to be used to the vocabulary that we use, because when you hear electrochemistry for the first time, and I remember when I was in grad school and I worked with electrochemistry because that was part of my PhD work, it was always backwards. It was always confusing. And the whole idea was because we're dealing with electron transfer, and electrons are negatively charged. Okay, so the species that gains electrons are going to be the ones that are going to be, you're gaining electrons, but you're the one that's being reduced. You're losing electrons, but you're the one that's being oxidized. Reducing agents are the oxidized species. Oxidizing agents are the reducing species. So you got to keep drilling that into your brain, because it's backwards vocabulary.